So welcome to the Enigma machine presentation, take two. Um, the goal of this presentation is to cover as many topics that I could think of that could be covered during the final exam. Regarding to the history of Enigma machine, I think the only important thing is that it started off as a commercial machine and only had three rotors to choose from. The military changed the design by adding the plug board, which will be explained later, and they added more rotor choices over the years. This is a look of Enigma machine from the outside. And if you just look at the machine itself, what happens is when you push down a key, as soon as the key is pushed down, the mechanical devices inside the machine would increment the rotor. It's usually the one that is on the most right will rotate upwards, and then something on the lamp board will light up. So the rotors that they rotate based on knock points. I said usually only the one on the most right would rotate. Sometimes the one on the most right and the one to its left would also rotate. So when you think about an odometer, the knock point kicks the next digit at 9. So at like say 09, it goes to 10, right? Both digits increase at the same time. Well, for an Enigma machine, the knock points are different depending on the rotor choices. So for 8 different rotors, they actually have different knock points. And as you can see in the chart, some rotors actually have 2 knock points. So for one full rotation, let's say if the one on the most right is rotor 6, for one whole rotation, the one in the middle would actually go up by 2 instead of just 1. All right, so that is a picture of a rotor. The inside, as you can see, is just circuits, and they are doing a permutation of all the 26 letters. So here's an example of how a letter gets affected by the different parts of the Enigma machine. And this is example that say for the plug board part, E is switched to N, and at the same time N must be switched to E. I is to G, where G is also to I. M is to A, and A is also to M. So let us assume that the button E is being pressed, then through the stecker or the plug board, that signal will be translated to N. And that signal will be waited to be translated by the third rotor from right to left. So let's say that that rotor translates N to N, which is possible. There's one way of permuting the letters. You can translate one letter to itself and becomes O by the second rotor, by V, and then it becomes W by the reflector. On the way back, W becomes M by the first rotor, becomes E by the second rotor, and eventually becomes P by the third rotor. Now at this point, the P should come back to the plug board or the stecker board, but since P was not one of the letters that we chose that was steckered, it was only EN Enigma, ENGIMA. So P was not included, so P will go to the output, and the lamp board where P will light up. So this is another picture that shows that the entire thing is just like a circuit. The reflector serves as the completion of the circuit. Now, the reflector itself is actually just 13 pairs of choices that maps one to another. So this is actually the reason why the Enigma machine could never map a letter to itself, because if it would, then the circuit wouldn't complete. The current would just go back to the keyboard where it is being pressed instead of the lamp board. There would be no output. And also at the same time, you can see the same state of the Enigma machine. When you have the input, it comes as a decrypt, but when you input the decrypt, the same current goes just in the reverse order. The lamp board would light up as the decrypt. And each state, as we say, is the choice of the rotor, the choice of the position of the rotor, the plug board, everything. Okay, we will talk about that in details later. Now, before we go there, we just talk a little bit more about the plugboard effect. I think this is probably the most important part. Let's say that we encrypt this string, this plain text, A, B, 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 using the rotors from left to right, rotor 1, rotor 2, rotor 3, and then we'll set the ring setting to AAA. All right. So don't worry about what exactly that means for now. Just think that's like vanilla, right? Just normal encryption without going through the plug board. That's what's important. So the first A encrypts to a B. The second A encrypts to a D, right? Because once you push that button, the rotor moves to the next position and it encrypts to a different letter. That's how it becomes polyalphabetic. This keeps going on, and you see, although it's the same letters from the plain text, it becomes different letters. Now let's compare that with the second row over here. So while you are encrypting with A to B without any plug board, with the plug board swapping A to B, A actually gets swapped to B by the plug board. But A encrypts to B at the same time implies B encrypts to A. So during the encryption without the plug board, that means the three rotors plus the reflector encrypts B to A. And this A gets affected by the plug board again and translates to B. While if you look at the second position, A encrypts to D. So over here, A by the plug board goes to B. B, well, it will just go to J, and J is not affected by the plug board, so the output is J. If you compare this with if we're using the plug board A and C, you will see that A encrypts to B. A by the plug board gets changed to B, and B just becomes Q. Well, B becomes Q, and Q is not affected by the plug board. And if you're interested, you can look at other example. Let's see over here. So over here, this B directly gets encrypted to I without being affected by the plug board. This B over here will first get affected by the plug board and be changed to A, and this A obviously will become K. Okay, I think that's enough for the plug board. Now, rotor settings effect. So the rotor settings comes in two parts, where there's a ring setting and there's a ground setting. So either of them is performed as a cyclic shift of the permutation. So when they're actually going through the rotor, they're just adding the ground value and subtracting it in the end, or minusing the ring value and adding them in the end. When it's on, this is the first pass from the right to left. On the second pass, which is from left to right, it just does the exact opposite thing. So the alternative names, the rotors themselves, sometimes is also be called drum and wheel. The ring settings, which is also called the static setting, will not be changed during the encryption during the operation of the Enigma machine, and they're called, in German it's called Ringstellung. The ground setting is also called the initial setting, is actually the thing that you see on the window of the Enigma machine, and that's the thing that's being increased every time you push a button. It's called the Grundstellung. There's the reflector, the plug board, also known as the Stecker board, and in German, Steckerbrett. So that concludes part 1 of the presentation. Okay, welcome to the part 2 of the presentation. We will continue on by talking about the key, or the different settings of the Enigma machine. So this is actually just specific to the naval M3 version of the Enigma machine. As we mentioned earlier about the history, throughout the years they added more and more rotors, more and more other fancy stuff, but M3 is somewhat in the middle standard, and relatively straightforward. So there's total 8 rotors for you to choose from a box. You could choose any of the 3 and put them in any order. So that is 8 choose 3 times 3 factorial. The ring setting is what you can rotate each drum before you putting them in. Again, that performs as a cyclic shift for the permutation. The permutation itself is designed by it's right limited by the hardware itself, but you can rotate it. So each one you can rotate it to 26 different positions, and you have 3 of them, so that's 26 to the power of 3. The initial settings also, the one that you see through the window, the ground setting. For us, for our problem, it was already specified that it will start with AAA. But in a real M3 machine, you actually have AAA all the way to ZZZ, which is, once again, 26 to the power of 3 choices. The reflector has 2 types. It's type B and type C. For our problem, it will specify that it's always type B. So it's 1 choice, but in the real world, it will be 2. The plug board, for us, the question specified it will be either 3 or 4 pairs of plug board. But in a real Enigma machine, since there's 26 letters, you can choose up to 13 pairs to use up all of them. And if you sum them up, there will be 2 to the power of 49 roughly. And for us, it's about 2 to the 28. The total number of things we do is 2 to the 50. For the real M3, it will be 2 to the 86. Now, the calculation of the 4 pairs, this very similar to 3 pairs, is 26 choose 8. You first choose the 8 letters out of 26. You will multiply that by 8 factorial, which means I permute all of them. I divide that by 4 factorial, means all the pairs would be the same choice, even if I change it differently. So that means, say, if I choose AB and CD, that is the same as choosing CD and then AB. It doesn't make a difference. And then for each pair, I would say AB is the same with BA. That's why I say 2 to the power of 4. So for each pair, if they flip, it's essentially the same. So breaking news, it's actually broken now. Instead of using brute force, so instead of avoiding brute force, what I decided to do is to just do it quickly. So what we initially did was actually try to make our language recognition very robust and try to recognize the somehow language of incomplete settings, like trying to play around with the plug board, but that didn't turn out so well. Though what turned out to be effective, what made me actually break the Enigma, is to just do it, but find more efficient ways to do it. So what was one of very important factor is only one-time calculation on the rotor effect is needed. So the ciphertext goes through the plug board and then the 3 rotors and then come back up the plug board. If I want to test that for a different plug board setting, actually I don't need the thing to go through 7 function calls, which is 3 rotors, the reflector, 3 rotors again, to calculate that value. I only need to calculate that once and save it somewhere and access that, and only that works for all the different plug board settings. One more thing is to check the crib position first. So the crib means a known text in the plain text, and for us that was KDB at the end of the ciphertext. So instead of deciphering the entire string and then check if the last position says KDB, we can actually rotate the rotors to a specific position, which is 64 for us, and then check if that encrypts to K. And if it is, then we will continue. If not, then we'll immediately break out. One more thing is we have to first check only 3 pairs and see if it is close enough. And only if it's good enough, we'll check the 4th pair. So how do we do this kind of somehow language recognition so quickly? It's actually, very importantly, the non-language recognition. So the low frequency letters in English is Z, Q, X, and J. All of them added together is actually less than 1%. So out of a string that is length 67, how many of them do you actually expect to see? Well, I set that threshold to 3. So if during this length of 67, if I see 3 of any of these 4 combined, then I will say, well, this is not English and reject it. And so this string will most of the case will not be checked for the entire length. And if it does, maybe it is English. I also implemented a common letter count, so the ENTORIAS plus H, all of them together added is actually about 60% of the frequency as a sum. So I will check if these added together, it will be that. So it'll be about half. I said at least half of 67, 33. So if it doesn't meet that count, then I will reject it and say it's not English. For more advanced language recognition, what we initially did and eventually will help us narrow down the candidates is the variance test, which is how far away from the standard, and the combination probability. So to say, TH is a common combination and ZZ is rare. So noting down these values, and then you can check for individual positions in the string, and you can do this analysis and see how close to real English do you expect it to be. But once again, this is much more computation demanding than the previous test that we're talking. If we just check, oh, this is the third Z I've seen, so it's not English, and I reject immediately without even needing to encrypt the entire string, makes the whole thing run much faster. All right, so some good things that we did, although didn't help us, wasn't good enough to help us success, was the plugboard generation method. So imagine in a scenario that K encrypts to W. Right, so our given ciphertext on the position that we expected to be K was a W. So how can this happen? Well, K can be staggered to A, and A encrypts to H. This middle row, by the way, is the exact 13 pairs of encryption for that specific position for a certain row order setting. So this K gets encrypted, gets plugboard affected to A gets encrypted to H is staggered to W. Well, that's one way to do it. Another way to do it is K to B, B to Y, Y to W. Now, if W is to W, that means there's no staggering for W. Well, then K gets staggered to D, D gets encrypted to W, W goes to W. Okay. So by this chart, I hope that you can see that we don't actually need to brute force all the plugboard settings, but only need to care about those that could potentially make K to be encrypted to W. And that is a lot less to test than if you were to brute force all of them. Let me clear the thing. And one more thing is distributed computing. So we could spread the number of keys through the different computers and let them run at the same time. Rounds of filter just means that we first did the loose language recognition, and then we save all the outputs, and then the second round will do a more accurate language checking. So in the end, very quickly, I will talk about what we did wrong and cause our failure. We spent too much time trying to solve the general case instead of taking full advantage of the crib. That actually heavily because we didn't realize that there was a crib uh, that was in the plain text, so we didn't just go that direction in the beginning, and we already dedicated a lot of our effort into trying to solve for just it could be any English sentence in there. So that's why we work towards that direction. When we realized that there was a crib, we didn't shift our effort fast enough um, into working around the crib. So that was a bad choice. We tried to optimize on the wrong things. We try to make language recognition faster instead of thinking about the right thing, which was turns out to be, how do you step through the brute force faster? Um, we assumed KDB wanted us to fail. We overestimated and complicated the problem. So at the beginning stage, we actually one of our group members said, "Hey, so in the movie it says, oh, every telegraph in the end it says Heil Hitler. Do you think Boklan would do something like say Hail KDB at the end of the text?" And I said, "No way, that is ridiculous. He would in no way make it so easy for us." And that was a really bad judgment. And of course, not reading the question carefully because that information should be implied in the question itself. Because otherwise, why would he say that was the agent with the initials KDB? And that concludes the presentation. Thank you for watching.